Thank you. Hi, everyone. Good afternoon. My name is Kaizad. I'm from Mission Control and happy to talk a bit about, I see my camera fluttering. Maybe I'll just turn it off. Happy to talk about some of the work we have done for enabling autonomy in a variety of lunar surface science and resource prospecting type missions. So before jumping in, I'll just give a quick intro to who we are as a company. So we've been around since 2015. We're based in Canada. We're focused on software technologies, and our team brings together expertise in other areas such as robotics, software, and operations. We have an indoor lunar analog testbed in our facility that we explicitly developed to generate high volumes of images of high visual fidelity lunar surface images rather than a digital simulator. So we could use those images in our AI and machine vision model training. We also have a test rover robotic arm test facility that we're constructing now so that we can validate some of the techniques we're developing and concepts of operations and all of that. Happy to share a few mission contributions this year. So we're doing an AI demo on the European Space Agency OPSAT, AI terrain classifier demo on the lunar surface, and supporting a lunar rover mission as well. So as probably all of you know, when you are thinking of designing a lunar mission, either on a rover or even if it's on a lander, there's a lot of challenges when it comes to understanding the lunar surface to inform mission operations. It's very important to understand the environment around you for hazard assessment, especially if you're doing navigation on a rover. It's important to generate a map of the surrounding environment, which aids in geological context definition, and also then understanding some of the key targets and features around you for collecting data for your instruments and other payloads. And in many upcoming missions, there's some limitations with onboard autonomy. And this introduces a high reliance on ground segment decision-making, which introduces high rover idle time. Overall, if you introduce several capabilities to add autonomy in the flight segment, this can enable the mission and rover to be more effective and productive overall, and perhaps also then reduce the operator workload in making decisions for several tasks. And I think this will become increasingly more important as more missions go to the moon and they're commercial in nature as well. So there's incentives to minimize the cost and maximize the science return and value for the various customers. So one of the solutions we've developed is a set of imaging autonomy techniques for lunar surface missions. And so you can think of when a rover or system captures images of the lunar surface, there are many features in that image that might be of interest to scientists, instrument operators, rover navigators alike. So our techniques essentially classify the different features in the images that can be also visually deciphered by a human, but this speeds up the process and then allows autonomy on board as well. And so once you can classify pixels in the image, you can also aggregate them onto a map, especially if you have a stereo camera to produce depth data that you can use to correspond to a map. And then this also becomes very useful for any mapping, path planning, GIS analyses. And then there's several use cases for using these data products both on board and in the ground segment. So I'll just, before talking about the use cases, a quick note. So we built a large data set of several thousand images and labeled them with the features with the collaboration with our science team, and used these images in a model training, validation, and optimization process. There's a lot of details here, of course, that I'm skipping out, but if anyone's interested, I can share more information. And then in the bottom right is an example output of our AI model that can classify some of the features here that we selected in our scheme, such as a crater exterior, interior, two classes of rock. They're not precise size classifications, but kind of relative from the perspective of the platform. And then just for the purpose of our data set, we also introduced the wall feature. A few slides about our use cases. So I think this could be really beneficial for autonomous targeting. So, let's say you have a thermal infrared imager that you would want to use to capture data across a variety of different types of craters. So as a rover is driving along, you could point your thermal imager to these craters if they're autonomously detected. And same with the multispectral imager or any instrument really. And if you have a LIPS, you could use that to target different types of rocks. And if you add this capability on board, then you're able to do this in a relatively continuous fashion as the rover is driving, so you save time compared to ground segment-based decision making. Another use case, so if you have several images being collected as the rover is driving from point A to point B, and of course, if you have a very constrained downlink capacity, you want to downlink just the higher priority data products at the start to inform some of the upcoming decisions and tactical cycles, then you can use this capability to identify and rank several features and then downlink the most important ones. A lot of this is the strategies here are similar to the Aegis system for Mars rovers, which some of you might be familiar with. And in the ground segment, if you have pre-annotated images, this can save a lot of time with a lot of tasks in operations. So if you have a specific object classified, you could pass it to other consoles. So in this mock-up here, you see you could potentially pick a particular object, submit it as a request for an instrument operator to collect data. And if you collect all of these objects in a database, you can do a lot of cool things like intelligent feature query. So if you're in the middle of operations and you want to see all the craters that have been imaged in the past 2 days, you could do that fairly quickly. You could add other measurements, data products, and metadata to those objects. And then, of course, integrating it into GIS if those features are geotagged to support mapping and other GIS analysis. And as mentioned before, a lot of these strategies have been proved in Mars exploration scenarios. So we're really building off success, demonstrated by NASA JPL in showing how autonomy can be introduced to onboard targeting systems. And as far as I'm aware, I think we're maybe the only organization replicating this for lunar exploration. So proving the technology and then also the ConOps. Just a few slides on some recent work that is in a similar domain. So recently we did a sensor fusion project. This was for a terrestrial project, as you can see in the example images, but we combined standard RGB imagery with multispectral in the visible near IR range, and then a long wave thermal IR, and used the combined data to train a model to classify terrain features and hazards that were of interest to a terrestrial vehicle. So something like this could be done again for lunar surface. Also, in the past couple of years, we completed a phase 0 study for essentially a thermal camera that could be integrated with some of the AI and computer vision techniques here for autonomous decision making, such as targeting two craters, for example. So this thermal imager is a sensor developed by our partner INO in Canada, and it's capable of sensing in 3 to 100 microns with a filter wheel that's designed for specific science investigations. So for our study, we were interested in a cold trap and water ice detection. This could also then support low light navigation, trafficability studies, other mineral ID studies. And right now we're potentially flying a variant of this on the Canadian Lunar rover, which is currently in phase A, but also happy to talk to anyone who's interested in the sensor for their missions.
2
We
minutes.
also did some work. Yeah, thank you. We also did some work in novelty detection. So this is a bit lower TRL, but essentially the idea here is to have a model that could pick out differences across a data set of images. So you might capture things that are not seen before or out of context or anomalies otherwise. And the goal is to pick these out so that operations teams have another handy tool. Otherwise, they may miss detecting this in very quick cycles. So I've just given some examples on the right of features that we had picked out in our study. Again, a lot of this is motivated from Mars rover operations challenges and some work done out of JPL to advance novelty detection. And we did some prototyping in our company and using our data set. So we have a couple papers out. Feel free to check it out. And then later this year and early next year, we're going to be collaborating with the science team of the Emirates Lunar mission, which is being led by the Mohammed bin Rashid Space Center. So our demo, which is funded partly by the Canadian Space Agency, will be supporting some of these operations. And of course, we also have a lot of interest in outreach and using our ground software platform. So just to quickly share how this looks from a high-level architecture. So rovers providing images to the lander that is streamed back to Earth, and our AI demo and processor is sitting on the lander and will classify images. The data products will then be used in the ground segment to inform path planning. And the last slide here, so just a highlight of different future applications that this could be translated to. So any sensor that's producing high volumes of data, such as a mass spectrometer or a hyperspectral sensor, there's definitely a need for data processing to extract the key features that investigator might need to know in real time. And so we're pretty keen to collaborate with anyone who sees a benefit for onboard data processing for sensors like this. In particular, the example on the left is from a paper we recently contributed to, Science Autonomy for Ocean Worlds Astrobiology. So I invite everyone who's interested in that topic to check it out. And so I'll just close with the final note. We're pretty excited to do the first demo of AI and machine vision on the lunar surface in 2023, and eager to collaborate with anyone who's interested in imaging autonomy for their missions. Thank you.
Perfect. Thank you very much. We do have time for 1 or 2 questions, if there's any. All right, there's one in the chat from Francisco. What are the computational requirements of the detection and classification algorithm? That's the first question. And the second is, go ahead.
Yeah, and I see, could rovers retrain on site with the features they're capturing? Yes, so online training is definitely possible. It's not something we're doing in our current demo because it requires a far more intensive computation than the actual inference. So right now we're just training on Earth using analog data, as well as I didn't mention, we're also training with some data from the Chang'e missions, which is published online freely from Chang'e 3 and 4. I think the plan may be to do one model update during our demo. In the future, of course, if there are processors that are available in the architecture to do more computation, then it may be possible to retrain on site. And I'll also quickly mention we're using the Xiphos Q7S processor for our AI demo on flight. So you can check out the specs. It's system on a chip with the Xilinx architecture.